Hello, I'm Jay, and I'm going to show you a sneak peek of Sirocco's course on extensions. This course is for people who want to understand extensions commonly used in the wild. In this section, we are going to cover commonly used extensions. Contrary to the rest of the course, not all the extensions in this section are logically connected. We are going to cover deriving-related extensions and a few unrelated extensions, which are all good to know and, personally speaking, some of my favorites. The first one, LambdaCase, is a nice archetype of the Haskell extension. Something so simple and innocent and yet so controversial. Writing /case instead of /result, case result of, saves us a few characters, time, and energy. We don't have to invent a unique variable name each time. In this example, we only introduce result variable to use and forget it immediately. What if there was already a result in scope? Would we use cleanup result, R? It's always cleaner to use LambdaCase and not worry. And the controversial bit comes from the fact that LambdaCase introduces yet another way to do something simple. Some developers are concerned that it can be confusing for beginners. And that's it. Let's talk about deriving. Here is a type definition with a type class deriving. We use deriving equals show to ask the compiler to derive equals and show instances for our type product. With standard Haskell, we can use standard deriving to derive standard type classes, such as eq, ord, enum, and others. But with these extensions, we can add more ways of deriving and more possible type classes. Now, let's look at these ways. The ways of deriving are called strategies. Currently, there are 4 available deriving strategies. Stock, and the stock means standard, which is a standard deriving strategy for the standard type classes. New type, which can be used with GeneralisedNewtypeDeriving extension. And AnyClass, which can be used with DerivingAnyClass extension. And the last one, Via, which can be used with DerivingVia extension. In some situations, the same type class can be derived via different strategies. In some situations, the same type class can be derived in multiple ways. When we use deriving, the compiler figures out how to generate the instances for us. How are these instances going to be derived? If the deriving strategy is not explicit, it's not instantly clear. DerivingStrategies extension allows us to control how instances should be derived. To manually specify a strategy, we need to add a strategy keyword after the deriving keyword. For example, we can make the original example more explicit. Note that we can have multiple deriving clauses with different strategies. For example, deriving stock generic and deriving new type eq, semigroup, and monoid. In some cases, you might want to use different strategies for deriving standard type classes, and we are going to discuss it next. We are going to take a closer look at GeneralisedNewtypeDeriving extension, which improves life quality when we are working with new types. But first, let's recap what new types are. The new type mechanism lets us create new distinct types by wrapping other types with no runtime overhead. It's a simple and accessible way to increase code type safety. For example, string new types, which reduce the number of ways we can shoot ourselves in the foot. With plain string arguments, it's quite easy to mix the types up. If we have some function reward with soup, which accepts employee name and soup as a text, we can either use parameters in the correct way or mix them up. In one case, it works as expected. In other case, we get a silly bug where we give the employee to the soup, but no compiler errors. On the contrary, the compiler does not allow to mix the new types. If we have a better type version of the function, it's not possible to mix the types up. Employee name and soup name are different types and cannot be used interchangeably. The compiler does not accept that. Although soup name has the same representation as a text, they are different types and have different type class instances. We can stock derive instances for equals, OR, enum, and bounded. We declare soup name new type and stock derive equals and show. It works. We can show the soup name. However, notice that the show instance includes the wrapper soup name around the string. Sometimes it's what we need, but sometimes we want the new type class instances to behave exactly the same way as the instance for the underlying type. For example, printing soup name to the debug output should be just a string. We can use the new type deriving to inherit new type instances from underlying representations. This time it prints soup name as if it's just a text string. Note that we are using deriving strategies to explicitly specify the strategy. On top of that, generalized new type deriving allows deriving of non-standard type classes, for example num. Here we declare a new type that wraps an int. We derive a num instance and can use numeric operators such as addition. And it won't be possible without this extension. The compiler complains that it cannot make a deriving instance of num non-fungible int because num is not stock derivable class, and suggests trying generalized new type deriving extension. We don't have to use generalized new type deriving extension with explicit strategies, but then it's up to the compiler to decide what and how to derive. For example, if we try to derive instance for the int new type without explicit strategy, we get a stock derive show, as we can see from the usage, but new type derive num, this can be confusing and not expected. When we derive a type class using AnyClass deriving, DHT generates an instance declaration with an empty implementation for all the methods. It's convenient if the instances can rely on the default definitions of methods. A lot of default implementations are based on the GHT generics. For example, from JSON and to JSON from ISON. Note that later in the course, we're going to cover generic derivation and these instances in more detail. Without DerivingAnyClass, we can declare instances with no bodies. Here we have two instances from JSON and to JSON. Just the heads, no bodies. It's the same as deriving this with DerivingAnyClass and deriving strategies. Instead of declaring from JSON and to JSON instances, we move them to deriving clause with AnyClass deriving strategy. DerivingAnyClass is also a controversial extension because it can mess up with the predefined or preferred strategies. For instance, generalized new type deriving. Just imagine getting an unexpected empty instance out of nowhere. Here we try to derive a new type num instance as we've done before, but this time num instance is empty because of DerivingAnyClass. The best part is that issue shows up in a runtime. Make sure to only use explicit AnyClass strategy with deriving strategies. When we derive a type class using Via strategy, we can ask the compiler to copy type class instances from another specified cursible type, meaning that these types have the same runtime representation. For example, new types or nested new types. DerivingVia is a more general strategy than generalized new type deriving, and in some sense more general than deriving any class. For example, we can explicitly specify the type int as a reference when deriving instances. We can go one step further and specify an instance based on another new type. For example, we can ask to derive the behavior for int from product or some new types. Non-fungible product int derives a semigroup instance via product that uses multiplication. Appending two 5 values of this type gives us 25, while the second instance is based on addition via sum. Appending 5 and 5 of these types gives us 10. On one hand, the default Haskell string is implemented as a linked list of characters and should be avoided at all costs. On the other hand, there are at least 4 performance-sensitive alternatives: strict text, lazy text, strict bystring, and lazy bystring. There is no string to rule them all, and we constantly have to convert between different strings. Overloaded string partially swaps this problem under the rug. Overloaded string extension changes the type of string literals from list of characters to a polymorphic type. String literals are now a call to fromString function, which is part of isString type class. How is it better and what does it give us? For example, if you use text, it's annoying to call pack on each call. Every time you want to create a text from a string literal, you have to pack it by hand for my text or your text, for example. Fortunately, text has an instance of isString. Overloaded strings allow us to use string literals to represent text with less boilerplate. We don't need to pack the text manually anymore. Note that we are using overloaded string extension for this reason throughout the course. In the same vein, overloaded strings come handy when dealing with byte strings. For example, if we use servant and decide to serve HTML and not just plain text or JSON, we have to add custom content type for returning HTML. First, we declare the data HTML, and then we write an instance for it. We write HTTP media type headers. We use these operators for parsing HTTP media type headers. This function works with byte string types. Without having overloaded strings, we would need to provide explicit conversions for all the byte string types, similar to what we've seen before, but with a bunch of calls to the pack function, which is manageable but still quite annoying. You can create an instance for a string type class for any other type, but it doesn't mean that you should. As the old saying goes, if all your types are strings, you don't have any type safety. Also, be careful when deriving isString. The problem is that we lose all the type safety because the type becomes interchangeable with other strings once again. Thank you for watching. If you enjoyed this lecture, make sure to check out the rest of the course on Sirocco.io.